Okay, so now that's me, and I'm going to talk yes, I'm going to talk about this report that was recently released. It was commissioned by the Public Prosecutor Office in Brazil in relation with the investigation they are carrying about this failure in Brumadinho. And the report has been co-authored by myself and Antonio Jens, who's a professor here at UPC. Then I need to acknowledge, before getting into anything else, that apart from Antonio and myself, well, there was a largest team here working. I will highlight some people. Well, first, the engineer, the policeman engineer, Leonardo Macedo, who came here to Barcelona to deliver most of the data and guide us through the intricacies of some of that data. And then people at the CINE team, in particular, Dr. Daniel Tarrago, who performed most of the simulations, and Luis Monforte, who helped with some particularly difficult simulations. And then external support from UNAM, Mexico, Miguel Angel Manica, and Professor Antonio Viana da Fonseca from Porto, who led the team that did some lab testing. Because, well, this study started as a numerical analysis, but then it became a bit more complicated. It was, as I said, commissioned by the Public Prosecutor Office. It was financed by Vale, because Vale had an agreement with the Public Prosecution Office to help them get them up to date into and to help them investigate anything that they wanted, really. And we were selected because we were identified as being independent of the many actors that have intervened previous to the failure. And the brief was to focus on the proximate cause of failure. It has to be technically oriented. I think we were not to identify faults on what has happened or anything such like. I think it was just what was the direct and proximate cause of this catastrophic failure. And there were several conditions as well coming along with the commission. And they, for instance, the study, the numerical analysis had to be based on Bentley, on Plaxis. And the reason for that was that well, it was intended for several of the investigators of the police to come here to Barcelona and be trained. And the idea was that something based in Plaxis would facilitate dissemination. Of course, I mean, those plans had to be changed, as many other plans, as many other things, because of the pandemic that hit, like when we were 3 months upon the study. But what we didn't change was this Plaxis focus. The study has been subject to, as per the contract, to external revision, and that there has been one round of revision. So what was released was a revised version of our work. And I have to mention that when shortly after we started, there was another review of this exact same problem that had come to the light. That was the expert panel review that was led by Dr. Robertson, and that was released. Okay, that was released like December 2019. And well, that was of great help to us, because I mean there was an enormous amount of work that was already done in that report. But it is true that the report concluded that identifying one particular reason for the failure, which is there is a combination of strains due to creep and rainfall, that we quickly disagreed with. So, but still, even if we disagreed with that conclusion, the report was useful, and that conclusion being there, that also was influential for the work we had to do. So I will first try to give you some background about the dam and its conditions, and then I will have a section on material characterization of the tailings, and then I will briefly describe the simulations. And of course, well, there is the report, as I said, that you can download. And as I understand, now the weather in Calgary is not ideal for outdoor activities. So if you're very curious, you can spend part of your winter nights reading the report. So, well, Dam P1, the Corrego de Feijão mine was the one that failed. The Corrego de Feijão mine was a medium-sized iron ore mine that was in a region in which there are many other iron ore mines, and it's slightly southwest of Belo Horizonte, which is the capital of Minas Gerais. The dam had been in operation for 40 years. Started operation in 1976 and ended operation in 2016. So almost 3 years before it failed. It was ended somewhere mid 2016 because the operation at Corrego had moved to a dry stack, and they didn't need any more a tailing dam. At closure, this dam was about 85 meters high and 700 meters along the crown. If you look at the profile of one section, more or less you work out that the average slope is almost 1 to 3, and it had been even steeper initially, and then at some time, I think at mid-90s, they decided to pull it back, and then the continuation, the subsequent stages were they had a lower slope. No? One important thing of this dam is that the older stages had very, very poor drainage. So practically there was no efficient drainage here in this area below the setback because of either how it was conceived or how it was built or the problems with sinter feed as a material for drains. The position in this dam had been taking place for most of the dam history by wide spacing spigoting. And you can see in this aerial view from 2002, I think that it reflects that kind of condition in which you have this radial beach starting here, and of course here there will be something that is not ideal for being in contact with the wall. Plus you have a significant body of water there as well. No? After 2006, a spray bar method was introduced, but at that time the dam was already almost finished, 80 meters high. No? That is a closer view of the timeline of how the dam was raised up. I have to say that Vale, which was the owner when the failure happened, took over this dam about 2001. This dam and the whole mine, of course. And at that time, the dam was already a pretty steep one and a pretty tall one. And you see, I have also marked here the timings of the Cpto campaigns. Why? Because probably, I mean, without Cpto, no one will have realized that the material in the dam was potentially liquefiable. The first campaign, the one in 2005, was relatively limited in scope, but already gave some indications on that respect. And you see that I don't know if it is related, but the rise sort of stops There was another campaign in 2016. Again, I don't know if it was directly related, but shortly after the dam was closed for operations, the results of that campaign were unequivocal in identifying a substantial amount of material that could eventually liquefy. And then there was another campaign, which we will talk about later, in just a few months before the failure took place. After the dam was closed in 2016, well, I mean, the activities that took place, well, essentially they were directed to drain the pool, to improve the runoff control measures on the side of the dam. And essentially they were seemingly achieving their purpose because, I mean, as you will see, the piezometers, there were many piezometers. That was well, there was a significant amount of instrumentation on dam B1. And there were, I think that the total number is close to 100, but it's true that many of those 100 piezometers that had been historically placed, not all of them were working. And of those that were working, some of them had erratic readings, etc. But still, I mean, there are around 25 piezometers that have a consistent history of readings between closure and failure. When you look at what that story tells you is that, well, I mean, the water control operations that were taking place were, well, seemingly effective, particularly above the setback, and not so much below the setback, but, well, the situation was one in which water levels inside the dam were slowly reducing, which is one of the things that when this this explanation came out was made us perplexed, because we were aware of that already. Then this thing, I mean, how come? And there were this particular statement here. This followed a number of years of increasing rainfall after closure. Actually, we didn't find that. And there were several gauges of measuring rainfall close to the dam. There was one actually at the offices of the dam, or very shortly, and this is the one that we are using because it had records going back to 75. And it's true that the resolution of this gauge was smaller than that of the daily and hourly resolution was smaller, but the other gauges that had a shorter time history. If you look at this record from 1975, that is when the dam was started, well, what you see is that in the 2 years after closure were among the driest on the record. And moreover, there is a slightly decreasing trend that makes those things not an oddity. And really they are not an oddity because, you know, in Minas Gerais, apart from mining, they grow coffee. And because they grow coffee, they are worried about climate change. And for instance, this is a study commissioned well before, I mean, those very dry years of the last decade. I mean, that was commissioned about this time when the first seriously dry year happened. And it concluded that in the area, climate change is going to produce a decreasing regime of precipitation. This is where the dam is. So that was already visible in 2011, and I think it has happened, it has continued afterwards. So what was going on apart from draining the pool? Well, the dam was, of course, in continuous observation. The presence of potentially liquefiable material was known, as I said, and there were stability analyses done by limit equilibrium. And you have one example there, and I'm not going to enter into if this number was something correct or this number of undrained strength ratio for the tailings was correct. The point is that everybody agreed that those results were suboptimal and that something should be done to improve the condition of the dam. Now the question was what? No, there was also an intention midterm to remine the dam because of reasons that will become clear in a minute. And a very highly qualified review panel endorsed measures 6 months before failure to improve drainage and to perform more site investigation and locate more instrumentation, because everybody was aware that any remining operation was going to be tricky. So this is what was attempted in the last year. And of them, I have to say that these ideas of improving drainage, I mean, the first idea was to try to perforate frontally drains at the setback and just in this area, in the lower area of the dam, deep horizontal drains up to 100-meter long that were meant to be perforated in, as we know, liquefiable silts. This is liquefiable silts which in a larger part were full of water. This is a very difficult task to perform, and the installation of those drains was not successful. And there were 30 planned, and only 14 were installed. The average length of those installed was half that initially planned, and essentially there were measures of flow of those 14. They did only a fraction of what they were intended to do. Moreover, the reason why this operation stopped is related to a particular drain, the one that is here in red, the DHP-15. DHP-15 almost, well, it could have failed the dam. It was a big scare, because during the installation, those drains were perforated with the aid of pressure, and there were what was localized outflows started to take place at some of the drainage vents close to the drain. There was a transient piezometric jam, and they weren't aware of this, of course, when they were doing the drain. I mean, no one did look at the seismic record of nearby stations, but after the big failure took place, there has been a beautiful analysis of those seismic records. And for instance, something that has been noted by the review panel was that the trace of the seismic record during that event of the failed deep drain installation is very similar to the initial trace of the day of the final failure. So there is a suspicion that on that occasion there was an event of contained liquefaction. Contained because, of course, the operation was stopped. The outlet of that drain was sandbagged, and after maybe a week, and all the fluxes stopped. The piezometers went back to normal, and life went back to normal. So what happened from that was in June 2018. What happened then later? What happened after the failure? The only thing that happened was that the site investigation and extra instrumentation campaign that had been planned to find more about the dam state and conditions was taking place. And I have to, the boreholes of these last site investigation campaigns were being done using wireline drilling and water circulation. Those drills, they didn't have automated registration of parameters of perforation or anything such like. The control of the pumping pressure of this water flow was done manually. There was this kind of activation in the machine, and interestingly, the last two boreholes that were perforated were the deepest ever drilled in the dam. They were very deep boreholes at 76 meters. This is why they were using wireline, because those are substantial boreholes, in this particular case, to install piezometers. The dam, without probably, was, of course, being observed by satellites. Not that that was being used as far as I'm aware, not that that was being used during operation of the dam, but after failure, all those acquisitions by different satellites have been looked into very intently. And I am sure that they will kept on being looked very intently. Initially, we thought that we were going to do ourselves one study, but as we were looking at this, I mean, more and more and more studies came out, apart from that of the original panel. So when 6 studies were already published, we thought that there was no point on performing yet another one. And the ones that probably are more comprehensive are that of the panel and that performed by an Australian team led by Holden. And those two more comprehensive in that they use different satellite streams, and they use a larger amount of data, particularly that of Holden. They both conclude, and we agree with their conclusion, that there is really no signal on the satellite stream about anything untoward happening in the phase before failure. This is an image from the Holden study in which they are plotting the signal to noise ratio. And when you are blue, your signal is like 5 times or 4 times that of noise, no? And when you're green, well, the signal is just too noisy to trust it. So you see that most areas in the dam really are just too noisy, whatever is the satellite that you consider. There are some spots here and there, and well, if you wish one, it's difficult to figure out anything from those spots, no? These I'm comparing here from 3 different studies that in principle are using the same data, Sentinel-1, Track 53, and in principle, they plot of different areas closely located at the foot of the dam. They plot their interpretations, and you see their interpretations offer a lot of well, different possibilities. No? So I think it's just too uncertain what satellites will tell you about what might have been going on here. Where the signal is clear at the rear of the dam, when you look at the satellites, what you see essentially is consolidation of the softer tailings or slimes that were still, well, I mean, settling after the dam had been closed 2 years and something before. No? One interesting thing of these areas in which the signal is clearer is that if you, the weather, even in dry, even if the year is dry or the year is wet, but the weather there in Brumadinho is very seasonal. So you have the rainy season, the dry season, the rainy season, the dry season, rainy season. Well, you see 3 rainy seasons, no significant effect on this trace, and that is a repeated fact when you look at this data. So apart from INSAR, there was some topographic data. There were some monuments that had been located here, not in the last bench, but in the one before the last. Those monuments have had the typical history of monuments in which the reference base is changed a couple of times. So when you look at the raw data, it is very noisy, but you can, if you skip those obvious jumps, then you're left with something that still seems very jumpy. This is settlement, of course, a small settlement, but it's not, it bears some relation with what we know. Because you see, this is the period in which the deep horizontal drains were being installed. And our interpretation of what happened here is that initially those drains were installed in a way in which there was a bit of, and there are records of discussions that also indicate that also that might be the case. They were initially installed without enough pressure, so there was a little bit of material lost through a drain installation, volume loss that was inducing some small settlement, a very small settlement. Then they started to raise the pressure of installation, and at some point they did actually reverse the settlement of the coronation. They were actually pumping a bit the dam, if you wish. No, that went out of hand, of course, with the incident I described before, which was followed by sudden settlement. That incident of contained liquefaction, and then you had the last 6 months in which essentially nothing happened. And well, after 6 months of nothing happening, failure. And you have seen this video a number of times, and I think I'm not going to repeat it because it's dramatic enough, and you have the image is probably clear in your mind. What I'd like to show you instead, and probably that will destroy my talk because I have to switch from one program to another, is a different video. There was another camera that was looking at the dam from the rear. You see, and it was a sunny day because it was summer in that southern hemisphere. And as you see, well, time passes, and if you look intently, you can see that the grass is rustled by the wind here and there, and nothing happens and nothing happens. And if we had more time, we would go through all these 6 or 7 minutes of seeing how the grass moves, and sometimes there is the shadow of well, something, I like the word of those things, a cloud, yeah, the shadow of a cloud passing, and yeah, nothing happens, and nothing happens, and you have this cloud here, yes, and nothing happens because we need to go to approximately, I think, please now look at this here. This is the top of the dam. You see, they hadn't really filled the last raising. There was a significant freeboard here, and I hope that sooner rather than later, yeah, you see how this whole section falls down, and it falls down, and it, as you know, it progresses, and it progresses towards the camera at with scary speed. I mean, you see that chunk moves now, and then there will be another chunk here very soon. You can start seeing the effects that you have seen on the other image. Probably you see still falling there a bit, but it's progressing here at the center in the dam towards where the camera lies. And you see massive slices, and this is the flow slide. It's already taking place. This is 1 minute before, after the beginning of the failure, as you know, and I'm going to hold it still for 10 seconds to see something. You see when the waves start passing in this area, which is also something, yeah, pretty impressive. I think that if there is, I know that it's difficult to define liquefaction, but if you come with a definition that doesn't include this, that definition is wrong. And now I'm back to my presentation. Be with me a second. So yeah, that's the front view, and the one that I have just shown you is the rear view. at exactly the same time. No? When you see that there is this sudden vertical motion at the top of the dam. So let's move now to another thing, which is material characterization. And let's start by well, this thing that was used for analysis. You have all this gray bit here, which is tailings. There were other materials. The foundation soils was a gneiss saprolite, and one good thing of the expert panel review was that they clearly identified that it was high quality foundation, and there was no way that thing could have failed. Then you have also the resins, and then the slimes at the rear of the dam. But the failure really essentially took place through the tailings. So the tailings at the front of the dam was something like this. And those are the materials in which I will focus on this talk. There was, of course, a lot of site investigation data from the history of the dam. But the historic data was, well, mostly from relatively shallow samples. And the main problem was that it had been unsystematic. You had a number of tests of different quality, but for instance, critical state line. And after that, that amount of data, then there was the campaign by the expert panel view, which had samples of very good quality, but they were a bit clustered. I will mention in a minute. Oh, someone is getting their car. Oh, sorry. And then the testing was extensive and it was systematic, but had some significant gaps. The first gap that we identified was that there was no systematic data on the strain rate effect, which, well, if failure was about creep, that was something that we thought, and we had to investigate it. If failure was really about creep, it was something that that we could really. We would not be able to do that with the information that was already available. So because of that reason and others that we discovered later, we decided to recover some samples from the dam ourselves with help mainly of Professor Antonio Viana that you see here. And that sampling with the help of the Federal Police are brave people. So they weren't scared to go deep into the ravines of the leftovers. So you see in this projected, everything is being sampled of the tailings, but you see how the red dots, they are relatively deep in the section of the dam. So presumably the tailings might have been more similar to those involved in the failure than those sampled before, for instance, by the expert review panel who had remained here in this area, relatively higher in the dam. No? Then when you look at this data, well, what are the tailings of Brumadinho? Well, there are like many other tailings. There are sandy silts and silty sands. Okay? And this is the historical data. And well, you see, there were more of the sandy silts, perhaps because they were, as I said, most of the samples were relatively superficial and close to the wall. The expert panel had taken some samples of at the rear of the dam to investigate the slimes. You see, the slimes are plastic, and they have at least 20% of clay material, and which are two traits that you don't see in any of the tailing samples. And those are the coarse samples as identified by the EPR. Those are the fine samples. Those are the grain size distributions of those that we took. You see, somewhere in the middle. When we had intact samples of Brumadinho tailings, But when you look at Brumadinho tailings intact samples, what do you see? You see these very thin interlayers of interstratified materials. See a bit of red and a bit of brown, and here a lot of black. If you were to test, well, we have tested a few, and I presume that more will follow, but I mean, the problem with testing any of these things is that each specimen will be different, and therefore it will be very difficult to try to create a picture with those tests together. So what we did, and also what the previous one did, was to create some reconstituted materials separating different fractions of the tailings. The criteria that was used in Porto was based in color. You see, the black, the red, the brown. That might have seemed a trivial criteria. You see, well, they seem to be more closely grouped than the previous one. And after you had created a sufficient amount of those homogenized material, then you create samples by moist damping, and then you do triaxial testing. No? But I was pointing that here you might think, oh, well, they are really too close if you look at their D50. But as it happens, D50 is not the end of the story, you see. The one single trait of Brumadinho tailings that is very different from other things is that they are very heavy. I mean, most of the tailings were made of iron, really, hematite and other oxides. So you see, it's a specific weight between 5 and 4. Those are the three materials from Porto. You see, they cover more or less the whole range that we have, from the heaviest to the less heavy. Whereas here, if you were to look at these chosen by D50, they more or less lie at the same average value. The same happened when you looked at the coefficient of uniformity. Somehow the materials in Porto, they cover the whole span. Whereas here, yes, they cover a larger range of D50, but I think coefficient of uniformity is a more important trait. Well, tailings at Brumadinho are very brittle, you know that. This is one example, and there are many. You are triaxial, isotropically compressed, then shear, you see, goes to 0. And you cannot have more brittle than this. Testing the sufficient number of triaxial specimens. If you follow the instructions, for instance, in the book by Jefferies and Bean, you will obtain critical state lines. Critical state lines, as you know, because you were here last week, had two projections. One of them is in the stress plane, in which you have the critical state line friction angle. And those are the results from Brumadinho. There are the blue and the orange. And you see they are here superposed on information from a variety of other tailings. And the thing to me is that this particular parameter doesn't change very much. This is not the case for the other projection of the critical state line, where those are just results for the different Brumadinho materials. And you see how the critical state line, the slope, maybe not so much, but the position of this critical state line in the compression plane varies significantly. When you look at what might explain those changes, well, it is not really D50. D50 doesn't correlate with the slope or the intercept of that critical state line in the compression plane. There are other things that, well, the slope doesn't vary very much, but things like the coefficient of uniformity or a specific surface will correlate better. Then those tests, they were failed in the laboratory. And one of the important things that you want to figure out from those tests is what is peak and drain strength. So you see, one limitation that we realized relatively late, but it was important, of the campaign that had been performed by the expert panel report was that they had relatively few tests in which undrained shear was taking place on the contractive side of the critical state line, that is for positive state parameters. So because they had few, they did trace this envelope that was also sustained by dilatant data up here. And here you see those are anisotropically consolidated, and those are isotropically consolidated, but you have something that joins them. Now, if you do a lot more tests, as we did, the picture changes. Those are the anisotropically consolidated tests. Those are the isotropically consolidated tests. You see the normalized peak strength ratio is very different for this type of test and for this type of test. And it does not really depend on the initial state parameter. You cannot trace a common envelope here. So that was a problem for the simulations that follow this approach. No? And you see, I haven't made a distinction here between the different materials that were tested, the different reference materials that have different critical state lines. They don't seem to affect so much the peak and drain strength, or at least much less than the previous consolidation path. Here I'm plotting again, this is the normalized undrained peak strength against the residual, also normalized by the well, if you wish, the vertical effective stress before shearing. No, you see again those those circles correspond to anisotropically consolidated things, and these empty ones, the empty symbols, to isotropically consolidated things, and that is the main distinction. But then it's true that when you look at the other axis, the color that indicates different material, well, starts to have some meaning. There are some tailings that were apparently in the laboratory that did attain lower residual strengths. What about creep? Well, there was a systematic effort at Porto to try to figure out if varying the strain rate will change anything. For instance, the peak strength. And you see very little changes. I mean, here we're changing the strain rate of shearing by 2 orders of magnitude. And the resultant change, even if here actually the things go up and down, but if you ignore that different materials are plotted together, the upper boundary will be 2% increase of normalized undrained strength per order of magnitude in change of rate of shearing. As a reference for moderate plastic clays, you have 10%. So we concluded that Brumadinho tailings are not viscous and that they will creep very little. It's not just laboratory testing. Of course, there is an impressive, there is 1 kilometer of Cpto in Brumadinho. And well, it's almost a big data problem, you see. I mean, those are just for the tailings. And you can sort of look that here there are more and here there are more. So you can sort of try to cluster by different means. What we did, one important thing also is that when you look at the traces of the Cptos, they are variable, they are highly variable. You have good widths and bad widths, but those variations are not fully random, really. If you plot here our guess estimate of and these estimates have carry an uncertainty of +1 at least a meter, no? Of when the position finish at different stages based on a fixed amount of free ball, no? So you see some of the stages really coincide very well with this these changes, no? And that is logical, because if you think how it was being deposited at every state change, those relatively few spigoting points will have been changed from one point to another. There might have been other changes at the same stage, but at least when the stage was changed, no? We decided to separate the tailings in two main groupings: fine here and coarse. And the basis for this division is a soil behavior type index of 2.85. That value has been chosen so that the things that we call coarse are those that you see here. This is the statistics, the cumulative distribution of parameter BQ for our coarse material and for our fine material. No? And you see that for the coarse, everything really is fully drained. The best separation that we did manage for this number, based on this, still had a bit of drained material in the fine, but only 20%. The rest had BQs that were quickly increasing up to values of 1 and more. No? So Cpto fine means not fully drained. Cpto coarse means fully drained. And when you have that criteria, you start separating the information and you apply common correlations. You quickly realize that the fine fraction, the one that was not fully drained, you see this is Olson and Stark normalized peak strength estimates. The fine fraction is bad. It's bad because the low limit of Olson and Stark central estimate is about here. So it's crashing against that limit. It's even clearer when you plot residual. Of course, Olson was based on case histories, and I suppose that in Brumadinho, that kind of analysis would have been impossible because there was not a relict feature to back analyze. So this is maybe an upper limit. There might be even lower resistances here. So fines were very bad. I mean, also you look at the state parameter, and this is a plus estimate. You have here the coarse, and you see the coarse. You may say, oh well, they are above. But hey, if you attended last lecture, which I hope by Mike DeFerris, he explained very clearly that the characteristic value is about 80%. So 80%, you see, you're very uncomfortably close to the, and this is liquefied here to the left. So even the coarse was in a situation that was far from ideal. But of course, the Cpto fines, those were catastrophic. Average 0.1. And even if you don't believe these higher values, because using North Sand, you will get something with the same average, but narrower, no? But still, terribly liquefiable. So how do we use that information to create a model? Look, this is a plan view of the dam. We have sections that later we will use for analysis. And then we have alignments here in red. I'm creating a grid of alignments. And the idea is that you will have this grid, and you will have a similar amount of Cpto data in each block that is created. So you can, well, I mean, distribute what you know more or less equally. And then on the vertical, you will consider layering according to the construction stages, for that reason that I presented before. So when you do that, you can have, if you wish, idealize sections of your dam in Excel, in which you can plot the number, the percent of Cpto fines on every particular block. And you see that some blocks in the alignments in this section, this is section 3, I think, here, and these blocks here are in good condition because they are green. They have very relatively few Cpto fines, but there are some blocks here that are awful. And once you have that distribution of how many Cpto fines you have in a particular area of a section, then we had to simplify that, because of course we cannot have Praxis doesn't have the ability to do something more subtle eventually, or not so subtle, like random field analysis. But we didn't want to have more than 3 materials for the tailings. So we came out with this criteria. If you have more than 50% of Cpto fines, that block, it qualifies as fine. If you have less than 10% of Cpto fines, that qualifies as coarse, and in between you have something. So, well, I will go now to the simulations, but I had here one section on bonding that I feel I need to talk about that, because on the expert panel review, there has been much emphasis on the Brumadinho tailings being bonded, and we don't believe that. But the argument deserves attention, and it refers to something related to what was observed on the triaxial test, also scanning electron images, and also data from in situ test. Well, scanning electron images, we did also some, and yes, if you zoom a lot, you will see that there is some bonding between particles. But if you zoom out, what you see is that you have a lot of unbonded contacts as well. So is the bonding that you see here also something that you might have created when you dry the sample to do this kind of inspection? Or how pervasive is that? What is the chemistry here? Well, those are things that we don't know yet. But more importantly, what are the mechanical consequences of having some particles that are, well, a collection of maybe smaller things? You see, when you look at the triaxial evidence, there might be other effects at play. This has been, the team at the University of Western Australia has been doing now some interesting testing in which you see they are creating moist tampered specimens of gold tailings at the same initial state parameter by 2 different procedures. One is what they call loose moist tamping, in which you create your specimen above the critical state line. The other is dense moist tamping, in which the specimen is created below the critical state line and then compressed to a situation in which it's loose. Those that had been created denser, they appear to have a much larger peak. So eventually you could, if you compare these with that, you could say, hey, there is some bonding there. But it's not really bonding. What is this trajectory? It's this trajectory of having been created denser, at least on those samples. That happened as well. This trajectory is also what is present in some of the specimens of which the panel have seen this more increased brittleness that they identify as a result of bonding. So this is a relation that I leave in doubt. I think that dense moist tamping might be also at play in those observations. When you look at the Cpto test, there is, of course, this graph by Professor Robertson, and I have plotted here the median values for all the tailings, coarse tailings, fine tailings. You see, if you look at the renal proposal, those really will be uncemented, and these will be borderline, but also outside the range of the renal database. So who knows? Who knows? Because this procedure, that is, it makes sense, but it's pretty indirect because it's based on a normalized tip resistance and data related to the G0, etc. There is a much direct way to look at bonding when you have shear waves. And that is based on very elementary observations that were, by the way, published at the Canadian Geotechnical Journal. You see, this is, here they are testing uncemented sand, then the same sand cemented, and they are seeing the effect of confining pressure on shear waves. Essentially, they are fitting the hardening parameters alpha and beta. You see that when you have uncemented sand, confining pressure does have an effect, increase your shear wave velocity. When you have as cemented sand, the same sand that has been cemented in the resonant column, that effect of pressure disappears. Those observations by Santa Marina co-workers, they have kept on doing similar observations in the last 2 decades. And now they have published these beautiful databases because they have observed that the 2 hardening parameters are related. Alpha is related to beta. And typically you will have clays here with large beta and low alpha, then sands. And here at the lower end, you have cemented materials with very low betas and very high alphas. We can compute hardening parameters using the soil and the seismic dilatometer data that was available in Brumadinho. Those will be your hardening parameters for that seismic dilatometer data. We can also compute hardening parameters for Bender element results on reconstituted triaxial samples. This is for the panel study. This is for those studies in Portland. When we do that and we plot all the results of Brumadinho against the database, where do they lie? Do they lie next to the cemented? No, they lie here in between sands and clays, as you will expect from silts. So our conclusion was that those silts were not really cemented significantly. So now I move to the last bit of my simulation, and I know I'm running late, but well, that will be relatively fast, because the first thing that I have to talk about is that we had to use Plaxis, and we obviously wanted to use something that was embedding critical state ideas. When we started with this project, North Sand was not available in Plaxis. And so we went for this model, the clay and sand model that was proposed by HiCU 20 years ago. And it's a model that we had had experience with other liquefaction problems, and that we had programmed in other, we had it even in Plaxis and had some advantages. This is a relatively simple elastoplastic isotropic critical state model. If you know CAM clay, from CAM clay to CASM, as we are using here in Brumadinho, there are very minor differences, but they are important. One of them is related to the plastic flow. This is the plastic flow that we're using is a non-associated. And that introduces a new parameter M, but that new parameter is interestingly, it's very easily related to K naught. And then there is your yield surface, in which 2 parameters N and R appear that they are not in CAM clay. In CAM clay, you will only have M. R and N, between the 2 of them, they really endow the model with the ability to have brittleness, because they control where the critical state intersects the yield surface, which is not anymore at the top as in CAM clay, and how steep is the fall to critical state from the top of your surface. So those are 2 key parameters. So still in total there are 7 parameters, and this is one advantage of CASM. The other advantage is that it was originally formulated precisely to model static liquefaction. And then it had the advantage that it can be easily extended. And we needed a model that could be extended to a viscoplastic case, because we wanted to look what creep will do to this case. So for that reason, there was a development of CASM, that is called CASM Visco, was created specifically for this problem. When you add viscosity, a viscoplastic element to CASM, what happens? Well, what happens is that you still liquefy, but you see the peak strength, the peak and drain strength in your path towards a critical state will depend on the rate of loading. You see, if you load very slowly, you will reach a lower peak strength than if you load very quickly. Well, CASM is no panacea. CASM has important limitations. It's not good for cyclic loading, but in this particular case, it's important to realize that because it's an isotropic model, it cannot account for induced anisotropy during consolidation. So you see those same material parameters, I am shearing from isotropic consolidation instead, or from anisotropic consolidation, I will get very similar peak and very similar brittleness. So it is essential when you're using a model that has this limitation to rely on what you think is more relevant of these two stress paths for the situation at hand. We thought that the more relevant path was the K-naught consolidation. So we were using this kind of simulation to match our test. No? The CAS requires some inputs as any other model. Those are the inputs, critical state parameters, elastic parameters, those that I mentioned before, and then overconsolidation ratio and initial state. We have recently worked out, and has been published by ICE recently, that for normally consolidated, say, tailings or materials such as this, these more complicated parameters can be advantageously substituted by things that you can figure out from, say, in situ testing. And then, but you will need also the initial state parameter. OCR by definition in this case is 1. So it can be made relatively simple. Still, you need something from the lab. So we need laboratory test results, and we need to link. You cannot do everything with in situ test yet. How to link the laboratory test results, the different materials, with our mapping of the dam based on Cpto. The link has been for us permeability. Because we could compute for every single grain size distribution the, say, a Coseni-Karman estimate of permeability, and then calibrate that against some permeability measurements on the lab. And permeability also can be linked, if you are able to simulate a Cpto, you can link it with the value of BQ. And we have said before that everything above BQ 0.01 is going to be our finds. So by these simulations, we are able to tell, okay, well, so those finds should have permeabilities of about 10. Those finds in the field, the Cpto finds, should have permeabilities around these values. So around here, so that should be more similar, say, to the brown Porto material than to this yellow material, the finds, say, from the panel. No? Anyway, those are. I should mention that how we obtain those BQ versus permeability, because there are these new technologies that you can simulate Cptos with reasonable constitutive models such as CAS. No? So you can compute your BQ, because that will be the ratio of these numbers that you're computing here and the numbers that you're computing in this thing. Well, this is not QN, this is sigma vertical, no? But you see the point. Anyway, ready to compute. Let's move at the simulations. And the reference models that we have used are plane strain models. Why are we using plane strain? To begin with, because of practical reasons. I mean, you cannot move to 3D to start. And second, if you look at this failure, at least these three sections are in here. That looks to me like pretty much, well, first approximation, reasonably bidimensional. So at section 3, there was the drilling, and I will pay particular attention to the situation in section 3. You see the different reference models, they have a different tailing material distributions according to that Cpto simplification that we have mentioned. And there are other materials, of course, the residual soil, the compacted fields, the drain material was also included for chimney drains and blackhead drains when they were present. Of course, apart from the calibrating CASP, you needed flow properties, because the simulations that we're going to, that is one good thing of Plaxis as it is now, that you can run proper coupled hydromechanical models. Also models in which the unsaturated part can be included automatically. You don't need to move from a flow model to a mechanical model. No, you can do it all together, which I think is advantageous. So for instance, the retention curves were modeled based on excellent experimental work done by the IPR panel. In general, the IPR modeling of flow, which was separate from the mechanical model, was top-notch. And we did examine, for instance, permeability in much detail, but we ended with taking the same values that they had used. So you have this thing that you will start building your dam, because what you want is you're using an elastoplastic model that is history dependent, and you will locate things initially with a particular state parameter, and that will change as you're building up the dam. So there are a number of stages they are in which consolidation is taking place, because those are coupled phases. You have we knew how long it took more or less for each one to be raised. So sorry, let me see if I can move further. Yeah, one particular interesting aspect is the hydraulic boundary condition. The pond extent had been also the history of pond extents. We did take it also from what the panel had found, the review panel had found. That was excellent work. We didn't agree, as I said, with what was the rain, but we did use different conditions. The base case was this one, in which the last 3 years were drier. Those are the data points that I showed you before. The last 3 years were drier, but we did also explore a very wet case, a what-if case. What would have happened to our model if the last 3 years would have rained as much as it did rain in the rainiest year, which had been 30 years ago? So what are the results? I mean, we are more interested in results in the period after dam closure, in which the only thing that is happening in the model is actually rain. Rain and consolidation, because you had still delayed consolidation from previous raisings. Interestingly, the settlements that are computed here is about 60 centimeters, and that is on the ballpark of the data that we have from INSAR in this area at the rear, where INSAR is more reliable. Note that in these historical simulations, all these delicate interventions of having a drain or doing a borehole, they are not simulated. We will talk about that later. You have pore pressure results that tell you a story. You see these different layers, they will have different permeabilities, and then you have these particularities of the zero pressure contour. If you wish, this is not really a water table because it enters and then goes down. Of course, there was a flow towards the face. Not very much, but there was flow. And there was an area that was unsaturated in this base case scenario. Not very much, but here it was. If this reference model with low rain in the last 3 years were verified against data from the water level indicators, the Cpto, the piezometers that were available, and more or less the results fit. Very similar results to the flow model in the expert panel that preceded, and it's not surprising because key properties are the same in both simulations. Only here we have consolidation. What about suction? Suction, well, you have some suction, of course, here in the unsaturated parts, Not very much, not very much. And the value, the top value, about 50 kPa, well, this is similar to what they got. Then, what if it had rained a lot in the last 3 years after closure? Well, if it had rained a lot, the dam will have saturated. But remember, we're running a couple models, so we can look at what are the displacement created by that super saturation of the last 3 years. And well, there is no failure. This converge, and you have here a bit of settlement, yes, of course, and here you have a motion in the area that was mostly unsaturated before, but there is no failure, no instability. Some motions because it will have saturated fully. What if the dam had been made with a material that crept, that had some creep? What if we simulate with CASMA, visco, instead of CASMA? Well, what happens essentially is that we're delaying consolidation where consolidation takes place in the slimes. No? I mean, nothing really interesting happens at the face when you add creep, when you add either calibrated creep effects or when you add extreme creep effects. What is extreme creep effects? Well, this is our laboratory results for strain rate. This is the calibrated creep that is more or less like the laboratory results. And this is an extreme creep, like if you were a plastic clay, say, and you had things that we didn't see in the laboratory, but well, anyway, thinking about that, we have come later to the conclusion that if there had been a large creep, maybe the dam would have still been there. Because large creep is favorable when you have a sudden shock. And that has been recently discussed at the Tailing and Mining Waste Conference that took place near to your town. Now we're coming to the last bit, which is triggering analysis. Triggering analysis are different, you know, when you address susceptibility. I don't know how to get rid of that. Yeah, when you address liquefaction, there is this step in which you address susceptibility, usually by doing some kind of Cpto study. And that is about the condition of a deposit. And if you're contracted, you're saturated, you're most susceptible to liquefaction. But that's not the same as triggering analysis. In triggering analysis, you try to identify if a potentially liquefiable deposit liquefy after some loading event. You have to identify an event, an hydromechanical loading event. And there are a variety of examples or possible triggers that have some kind of replicas in the laboratory. Now, and we're coming here to the Brumadinho problem. The Brumadinho problem is that we couldn't find a trigger for a long time. There had been no incremental loads. There was an excellent seismological study proving that there were no earthquakes. There had been no significant blasting that day. There had been no obvious slope erosion or foundation failure. Internal erosion, you see, for a while we were clinging to the hope that this single isolated photograph for one day of an inspection report will explain the failure. That was 6 months before failure, and it was never repeated, that kind of observation. I think it was related to the issue with the failed installation of the drain. And as for pore pressure increase, general raising water level, no, it was going down. Drainage malfunction, it had been as it was from always. And what about creep? Well, creep, you know, creep, there are those experiments in which you see triaxial testing that has been published as well, by the way, on the Canadian Geotechnical Journal. Is marine dredge sand loose, and you see the isotropic consolidation, then shearing. They come to A, there is creep to B, then they come back to A, more stress obliquity. They creep again, and in this creep path, boom, it fails to liquefaction. So someone can say, here creep has triggered liquefaction. And I will say, no. What has triggered liquefaction there is that the drainage line was closed at point C. The ability to creep of the soil is like the fact that this instability line is here. That is a result of what is the initial state, of what is other properties. Is the ability of a soil to creep is not a trigger, it's a conditioning factor. So we didn't believe on that as a trigger. And finally, well, maybe the trigger was hidden in plain sight. There was another review that was only for Vale. It was more focused on organizational issues related to this failure. But there was a very interesting comment that was made in that review, which was in Portuguese. And they said, well, you know, it's true that the previous mechanical review had discarded this as a possible trigger, and also it seems relatively small, but it's true that they were drilling there. And when you look at where it is positioned, it is suspiciously centered where things start happening. And this is true. It's suspiciously centered when things start happening. The borehole that was drilled that day, I said already, it was one of the deepest ever drilled in the dam. And when after simulating the flow, you see this is the zero pore pressure condition. If you're drilling a borehole here and you're drilling it with water, you have increased around the borehole your pore pressure, but all this stretch. And this is a very tall dam, and this is at close to 300 kPa. So that started to become suspicious. So we performed one analysis using CAS, a conceptual analysis, in which we were trying to look if it was possible by borehole overpressure. You have an axisymmetric model, and here close to the wall, we're going to raise suddenly pore pressure, and then we're this is again model hydromechanically coupled model, no? And we see what happens. And what happens is that that liquefaction takes place around the borehole at distances of up to half a meter around the borehole. And of course, it will depend on the relation of how fast is this rise related to the permeability of the material. If the material is more impermeable, it will be more likely for something like this to happen. Now, that last borehole, at the bottom, we have a Cpto next to it. And at the bottom of the dam, there was about one of the worst areas in which more concentrated amount of fine material was present, Cpto fine material. There had been a precedent borehole, almost the same increase in pore pressure, almost as deep. But that one had a condition that was not as bad as this one. You didn't have 12 meters of highly impermeable liquefiable material. You had some drainage layers there. So anyway, we had at least one candidate, so let's try it. We're going now to see what happens to the model when we liquefy one of these tiny bits here. A cluster 1 meter by 3 meter around the borehole. We liquefy by in CAS, reducing parameters N and R. And we're going to see what happens, because whatever it happens, if it happens, happen very quickly. You have seen the failure. So the model now is going to be undrained. So what happens? Let's see if this thing works, because typically it won't work. But yeah, you see something starts happening there. Something propagates, and then falls down. And the kind of failure that you see here, it has some features that are very much like the ones we have seen in the videos, that the front of the dam moves horizontally in advance, that you have a larger settlement here at the crest. No? So that is plausible. And also, of course, I mean, we are doing 2D analysis. So that's not a borehole. Borehole is limited in the direction perpendicular to that 2D analysis. So we did something like it's not a full 3D of the dam. We just simulated if the 3D-dimensionality of this initial liquefaction trigger made an effect on that failure. So in passing, let me just say that 3D Plaxis does not include effects such as rain and such like. So it is advantageous in some respect, but it would have been complicated to run the similar analysis using 3D Plaxis. No? Well, what happened is that yes, you had the same kind of failure in this 3 model, in which the only thing that starts liquefaction is this tiny bit here. You see the scale? It's sobering. We're looking forward to move that into a full 3D. Right? That will be demanding computationally, because again, you see the size of what is triggering the failure. No? We did also some analysis to see in other section, the penultimate borehole, what happens if we liquefy that? Well, what happens is that because of the material distribution is different, you don't, well, liquefaction is contained. It doesn't turn out into a failure, a full failure at the dam phase. Same if we try to reproduce the event of that failed deep horizontal drain. It was closer to the front, the materials were better here, and well, there was a bit of liquefaction, but it was contained. So I'm concluding with some lessons learned. And the more obvious perhaps is that you shouldn't drill with water in a liquefiable material. Others is that if you're going to analyze triggering, you should use critical state models. They give a lot of insight. And you should use coupled hydromechanical modeling. And also, something that I have taken from this study is that we need to be humble, because we have now a working hypothesis, but this thing, liquefaction is an unstable phenomena, and I really won't be surprised if we are corrected in due course. And from a larger point of view, well, if you consider that this kind of analysis will move into regulation and more people will use it into standards, and there will have to be a lot of thinking about where to, if you're going to analyze hazard, you will need to think about where to place the uncertainty in your models. And I have some suggestions for that, but I have been spoken just for too long. So probably everybody has left already, and I'm finished. Thank you for being there. And I can come back to this later. Are you still there? I should stop sharing my screen, no? Yeah.
Great. Okay, thanks very much, Marcos, for that talk. We are about 15 minutes over, as you mentioned, and I see a lot of questions coming into the chat. So not to put you on the spot, but we could, compile all the questions, potentially send them to you, and you can answer them at your leisure, and we post them with the video. Is that okay with you?
That is correct, and I will try to answer more briefly than present.
Okay, yeah, because I just there's many questions.
Just, let me just emphasize that that has been a very fast run through what is a large report that is available for everybody to go and peek into and well discuss with us. Thank you for having me here.
That's great. Well,
there is one. Just let me just answer to this thing that has come. Is the CAS model available in Plaxis? We are in conversations with Plaxis so as they will make it more safe to use, because now it is available from me. If you ask me, I will send it to you, and I have done that with everybody that has asked. It's a DLL, you can use it. But it will. The idea is that to make it more robust things like units and other such like. And for that, we're planning to do that alongside Bentley in the next few months. So it will be released next year or something like that.
Okay, great. Well, yeah, thanks again, Marcos, for being so generous with your time and agreeing to discuss the reports or the results of your report. We really appreciate it here at the Calgary Geotechnical Society, and thanks everyone for joining.